Yeah, thanks a lot. Well, thanks a lot for the invitation. It's very nice to be part of the workshop and part of the thematic year. And just to repeat what everyone has said, yeah, it's a shame not to be there, but okay. Let's move on emotionally and let's see how the talk goes. So yeah, just okay. So let's try to discuss. Just feel free to interrupt at any point. And definitely feel free to contact either, well, myself or Xavi, who's my collaborator, Francisco Javier Martínez Aguinaga, he's in Madrid. So yeah, we would be very happy to receive an email from you if you're interested in this kind of story and you have some questions or you just want to chat. Okay, so yeah, I'm gonna talk about this idea that we have that we call ampleness up to avoidance. And the elevator pitch for this is basically the following thing. So the thing is, okay, we like kind of Gromov's convex integration. And this roughly says that if I have a differential relation R that is open and ample, then the H principle applies because convex integration applies. And as many people have repeated over and over this week, this means that basically we're able to say something about the weak, let's say the weak homotopy type of the space of solutions of this relation by relating it to its formal counterpart. We will discuss what this is later on. There's plenty of examples that, okay, Gromov worked out, for instance, in his book or in his original paper. So, okay, inversions in the subcritical dimension, they abide by this scheme. Free maps outside of the critical dimension, yeah, okay, linearly independent tuples of exact K forms where K is not one or volumes. Later on, McDuff used it to classify even contact structures, which are maximally non-integrable hyperplane fields in even dimensions. So unlike contact structures, these things are completely flexible. And okay, these are all nice results, but further, I mean, convex integration is just a nice tool if you are into H principle stuff. And basically, in many cases, I mean, it doesn't prove what you want, but it gets you kind of a bit there, right? So use it as some preliminary, like as a manner of simplifying your problem. So for instance, Emmy in her loose Legendrians paper, for instance, the first thing she does is she uses it to pass from formula Legendrians to things that are epsilon tangent to the contact structure. So they form like epsilon angle with it. And then she can do further things to really kind of flatten them out to actual Legendrians. Okay, so yeah, so we like convex integration. That's all fine. And okay, so what is the, so as you may know, I have some kind of weird obsession with maximally non-integrable distributions. And something that I've been thinking about kind of for a while is kind of like, okay, yeah, where's the flexibility versus rigidity line in general? And kind of, I guess like in 2 or 3 years ago, I started thinking that it would be just a good idea to say, okay, let's kind of go through all the pairs Kn, where K is a rank and N is a dimension. And let's just try to, well, check ampleness, right? And let's try to just kind of list out kind of when ampleness works and when it doesn't work. And my expectation, which was kind of naive in retrospect, is that, okay, in some cases you would just get ampleness kind of easily and therefore flexibility. And then you would be like, okay, happy you proved a thing, but sad that, okay, there's nothing interesting. And more importantly, you would see that kind of like some things are maybe, yeah, I don't know, I'm going to write it like this, very not ample, maybe. So you would just see that, oh, kind of ampleness fails kind of badly. And then you think, oh, maybe in this rank and dimension, maybe I have rigidity. So the idea is, right, is to try to pinpoint where rigidity may be by just testing flexibility.
How maximal are you maximal? Is this kind of?
Yeah, that's a good question, but I'm not going to tell you yet. I'm going to tell you later. Okay. Okay, and yeah, okay. So maybe just, okay, maybe naive thing. I mean, so the first thing is that it is actually not so easy. Like if you give me a random K and a random N telling you what maximally non-integrable is, it's kind of non-trivial geometry or linear algebra, in fact. So I will elaborate on this. But also more interestingly, perhaps, is that kind of as we started testing pairs Kn, what we saw is that there's kind of some kind of funny middle ground, which is like kinda. So it's kind of like you check ampleness and it kind of almost works. And okay, I will be precise about this, but what I mean is that for most principal subspaces it works. And then there's some sub-variety of principal subspaces for which it doesn't. And then you're kind of a bit disappointed because kind of if you just want to apply Gromov's kind of black box, then that's the end of the story. But it kind of seems that it is pretty close. And okay, this is what the talk is about. The talk is about when we can make this work. So basically, we give a criterion that we call ampleness up to avoidance. It is more general than ampleness. And you should imagine that it basically says, okay, in some cases, if you're almost ample, then you can still make convex integration work. Okay, so this is the pitch. And maybe, okay, this you will see during the proof, but the thing is that we don't need to kind of do convex integration from kind of the ground up. What we do is kind of we build some sort of H-principle thing on top of convex integration that allows us to reduce to the classic story. And maybe just to give you a flavor, so the way it works is that given a formal solution, F, what we do is we produce, so this R is ample up to avoidance. We produce a new relation that is inside of R. It's a smaller, we build it out of R by carving out things in a clever, well, I don't know if clever, it's actually in a quite naive way in some sense. And F is still a formal solution of this, but now this is ample in coordinate directions. So basically for every F, you have to carve out in a different way, but we will see. Okay, so what is the plan of the talk? The plan of the talk is that I will spend a ridiculous amount of time recapping Gromov's convex integration, and this may be a waste of time because maybe 80% of the people know about this, but okay, I think I want to keep maybe the 20% alive. And after we've gone through the basics, and this will help me set some notation, I will talk about ampleness, about examples, and I will answer Yasha's question of what is maximally non-integrable for me. Okay. So let me recap the story. So as per usual, we have a bundle E on top of a smooth manifold M, and we're interested in sections of E that satisfy some differential constraint, let's say of order R, and the way in which that I guess dates back to Cartan or something. The way in which you can encode this is as follows. You say, okay, let's take F, and out of F, you should build an object that we call the R-jet. That is basically at every point, you take the Taylor polynomial of F or degree R. And kind of tautologically by construction, whatever this is, it's a section of a bundle that we call the bundle of R-jets, and I denote as JRE. And this is the bundle of Taylor polynomials of sections of E. Okay, so we have all the Taylor polynomials at all points. And now I have my favorite Taylor polynomials, and these I call R. And now basically, if I say F is a solution of R, this is the same as saying, well, if I take the Taylor polynomial, it takes values always in the subset R. Okay. Cool. So this is what we want to do. We want to construct things like this or like this. And what Gromov, well, I mean, this is kind of a general H-principle philosophy, but I mean, what Gromov said is, well, imagine that instead of this diagram, we have a different diagram where at each point we have some big F that is such a good Taylor polynomial. You're just giving solutions individually at each point. And what Gromov proves is some sort of like infinitesimal to global statement. So he says, if at every point you can give me a Taylor polynomial of solution, and these things vary smoothly or something or continuously, then, okay, this is kind of on the nose, this is not a global solution, but up to homotopy it is. You can homotope it to a true solution. So the statement is, okay, here I have big F, here I have little f, which is kind of the zero order part of big F. And what I'm claiming is, well, what Gromov is proving is that if R is open and ample, and we will discuss this a lot later on, then you can deform little f and big F to, well, to some h such that h is close to little f, and the Taylor polynomials of h are homotopic to the big F given by to you. Okay, hopefully nobody's scared of this since this has been going on all week. So, okay, so my plan is, I mean, I want to get into the guts of convex integration a bit. So I will do the mandatory examples. So
you are dealing with relations of some order R. R can be bigger than 1.
Yes.
Yeah,
yes, but I mean, at some point, so yes. I don't want to explain the general scheme. So actually, at some point, I will just say R is equal to 1. And okay, I just do this for simplicity. The story is kind of quite similar for higher order. It's just inductive in order in some sense. Okay, so mandatory example. A sample problem is the following. You want to construct immersed curves in a Riemannian manifold N that are isometrically immersed. And okay, so I fix, okay, I call I the source of these curves, and this is also a Riemannian manifold of dimension 1 that is parameterized by length, just for simplicity. And then basically what we're saying is that you have Tn, right? These are all the possible velocities a curve could have. And the subset I really love is the sphere bundle, right? The unit vectors. And the problem says the following. It says, well, give me a random curve. It can be anything. And at each point of this curve, give me a vector of unit length. And the question is, okay, can I find an isometrically embedded curve H that is close to little f and whose derivative that should be of unit length should be homotopic to f? Okay, so okay, maybe random picture of f. So f is terrible, maybe. So maybe it stops or something, and then it has singularities. I don't know. So this is f, but okay, at every point at least, we are keeping track of what the desired homotopy class of the derivative should be, and this is big F. Okay, and I want to find some H close to this. So okay, can you do this? And okay, so the answer in general, of course, is no. So the point, right, is that you could have an F that is too fast. Right, so you could have an F that is just going across N at super high speed, and then okay, H is just trying to keep up at speed 1, but H is quite sad because okay, it cannot go faster than 1. So okay, it cannot follow F. Okay, the end. But more interestingly, right, if f prime is short, what's that? So if f is short, meaning that f prime is not too large, is at most unit length, then you can do it. And the proof is this picture. Right, this is what you do sometimes when you're like riding a bike and you're like following someone that is walking, right? You just kind of zigzag around them in an awkward manner. So, and of course, you may be quite creative, right? And you could zigzag in more complicated ways, depending on how bored you are. But the important thing is that you stay close. So, okay, these are possible H. Okay, so, okay, this is a clearly convincing argument, but because you do this often, maybe, depending on how much you bike. But, okay, let's give an actual argument.
You want the derivative being in the disk or in the interior of the disk?
So for, I mean, okay, so if I was doing kind of things like Nash's isometric immersions, I would want it to be inside, but for curves, it really doesn't matter.
Really? I mean, you have to.
I think
you have to increase the length or not.
No.
To get
where it's 1, you just keep it.
Yeah, exactly. I mean, right? Yeah, I mean, basically, when f prime has unit length, I just do f prime, and everywhere else, I just waste time.
Yeah, that's what I mean.
I mean, if the big F is pointing outside, you need a little bit of space to travel, no? Indeed. Okay. Yeah. If it's derivative 1 everywhere, then
yeah, that's what I mean.
Yeah, you probably need it to be at least smaller somewhere. Yeah. I think,
well, but I mean, okay, we are saying that it's 0 close, right? I mean, okay, you mean like that it may not close up or something like this.
Yes, but it might not be homogeneous.
Sure. So okay, maybe right. Okay,
yeah.
Sure. Okay, I agree that maybe if f is doing some sort of weird zigzagging and this it's a closed curve, maybe I'm unable to close at the very end or something like this. I agree. Okay, I don't want to worry about this, but okay, sure. I guess if f prime everywhere has unit length, then there's some problem to close for closing. Sure, I agree. But okay, so okay, then I'm gonna put this. Okay.
Yeah.
Perfect. Okay, so now, okay, so maybe let me kind of point something out. So okay, in order to construct H, there's kind of 3 things I want, right? So I want isometry, I want C0 closed, and I want homotopic to big F. And the first claim, okay, I think yeah, everyone knows this. But okay, I'm sorry. The claim, right, is that isometry is actually quite easy. What you do is you say, okay, let's not even attempt to construct H in the first place. Let's just construct the derivative first. And basically, you just make the choice like, okay, I will just make the derivative kind of 1 everywhere. And it doesn't matter like what you choose. Certainly, whatever you produce is isometrically embedded. And then H is obtained from H prime by integration. Now, of course, the thing is that, okay, we want to do isometry while keeping the other two conditions. So for this, let me do a picture. So, okay, so here I'm gonna draw Tn at one point, right? And this is the space of all possible velocities. Inside, I have my favorite velocities, which are the unit ones. This was the relation. Because I'm short, and okay, now, okay, I'm like, okay, I'm really very short. I'm really inside. Okay, fair enough. F prime t is here or something. And we also have the formal data, which must lie somewhere in the sphere. I'm gonna, for simplicity of drawing, I'm putting it here. And now all we are saying is the following. The ball, right, is the convex hull of its boundary. So in particular, F prime is a convex combination of a bunch of vectors in the boundary. You can choose them quite freely for this kind of thing. But in this case, for instance, the typical choice that will produce the sinusoid I made before are these two. And now I guess if you were like a control theorist, you would be perfectly happy. You would produce kind of just like a Lipschitz curve that spends half the time with this velocity and the other half of the time with this velocity, and it just jumps. But since we're doing kind of topology, we want to produce a smooth stuff. Okay, so let's say kind of a priori control theoretically in a way, you would just say, okay, I'm gonna put this a bit lower. I'm gonna be A1 kind of for roughly, well, let's say exactly half the time somehow, and A2 for another half the time. But okay, because we are like smooth people, we want to smooth things out. And the way to do it is you say, well, I mean, the sphere is connected, so I can connect these two controls, these two values. And the good way to do it is to do it through F, because then you will stay in the class of big F. So I fix two paths like this that connect to Ft, which is kind of an anchor of what I'm doing. And now you say, okay, I kind of use my anchor, but I spend barely no time there. Then I travel to A1 very fast. I spend half the time. Then I go back to F, and then I do nu2 to go to A2. All of this I do super fast. And then I go back finally to F. And okay, if you do these things kind of carefully, parameterizing these paths properly, then okay, this is smooth, which implies that H itself is smooth. You're in the correct homotopy class because you're using this F as some sort of anchor, and you're kind of growing tentacles that go to the controls A1 and A2. And furthermore, you're C0 close. And okay, I will just do the typical picture. So here's F. And what we've done upon integrating this thing, kind of you start at F, and then you switch to A1 very fast, and then you switch very fast to A2, and then you switch very fast. And for instance, okay, I guess because we are not analysts, kind of we don't care how fast the switching is, so you try to make the switching very fast or something, and so you get kind of maybe a very sharp thing kind of. But because we're not taking limits of stuff, it doesn't matter. And the important thing, of course, is that if I want to achieve C0 closeness, all I have to do is kind of just increase the frequency of the switching. Okay, I'm just not good at drawing this, I'm sorry. Okay, so this is the proof, right? In order to produce a solution, you just build a highly oscillatory thing that wastes time around it. Okay, so now basically verbatim, the same proof translates to the following more general control problem. You just have, okay, a target manifold N still, a one-dimensional manifold I, and it is still inside of all the possible velocities that my curves may have. I have a favorite subset, which I still call R, but now R is whatever, before it was the unit sphere. And the question is the same, given a formal solution, can I find a true solution nearby? And okay, and now this is where ampleness comes in. So basically, if the relation is so-called ample, then you're fine. And what does ampleness say? It says, okay, here, let's fix a point P, or let's look at all the points P. And at each point, you look at all the possible velocities. And inside of all the possible velocities, you have the allowed ones, the ones you like. And now the point is, okay, this set before it was connected in the case of the unit sphere, but in general, it may have several path components. And what you want is that each path component, its convex hull is the whole thing. And okay, basically, if you have this, then you are happy. And the reason, sorry, too fast, is that you can do the same picture as before. So we can always just draw the same thing. So here you have the tangent space at a point. Somewhere here is f prime. Somewhere, I don't know, far away, maybe is ft. And now we have no idea what RP looks like, but certainly what we know is that if I take the connected component of RP, RFT, containing FT, then okay, whatever it is, it must be kind of big enough so that its convex hull contains this one vector. So okay, here's FT. This is inside RFT, and this is the connected component that contains big FT. And basically, because of this ampleness assumption, then it means that, okay, we have a bunch of vectors whose convex hull is this thing. Let's call them things, A1, A2, A3. Let's say, and what we're saying is that f prime t is a weighted sum of these things. And the proof is the same. You still use f as an anchor. You spend some time in A1. You spend time omega 1. Then you go to A2, you spend time omega 2, and then A3, and then you iterate this fast. And the faster you iterate, the more oscillatory you are, the better you approximate F. Okay, so at this point, we're experts in one-dimensional convex integration. I guess everyone is happy. Does anyone have complaints? Okay. Cool. So again, let me do typical pictures just to make sure we're all on the same page. So let's draw typical examples of sets that are ample. So in what I was doing before, I had defined space TFTN, which, okay, now it's called A, and the role of B was played by this RFT. And okay, typical things. So, okay, here is A. Let's say I give you B as the complement of a singularity of something of codimension 2. Then B, the complement, is ample, right? Because this is in what you're missing is in the convex hull of everything else. Typical example that is not ample is when you have a codimension 1 singularity that is linear. So a hyperplane. Then you have the complement is 2 components. Each of them is convex by itself, so they are not, well, it's not ample. A typical example where this is relevant is, for instance, when you're looking at one-dimensional stuff. So if you have one-dimensional stuff and you have a non-trivial singularity, then essentially everything is bad. So no. And okay, maybe let me say that in this business, kind of when you're studying relations, the typical thing is that you'll have kind of a differential relation given as a complement of some algebraic set variety or something like this. So for instance, typical thing that you may see, maybe it's like a cubic. And then in this case, the cubic itself is ample and the 2 components in the complement are ample. And I will do one example that will appear at the very end when I do applications of what we are doing. And this appeared as the limit case in what Melanie was doing the other day, I believe, which is a cone, and let's say in dimension 3. So if I have this cone, then the interior, the 2 components in the interior are bad, but the outside is good. Okay. Okay. So okay. How am I doing time-wise? I think bad. Okay. Well, let's see. Okay. Amazing. Okay. So we've done the one-dimensional case. Let's kind of try to prove the general case extremely fast. And now, for simplicity, I'm doing kind of J1, but again, it's not essential. You can do it in general. And in fact, when we do ampleness, we don't care. We do it in general, as Gromov does in his book. So, okay, the problem is as well what we've already explained, and the question is, okay, what is even ampleness? And the idea, right, is that basically you only know how to do one thing, which is how to do the one-dimensional case. So you just reduce to that case. And let me do the picture. So let's say here is M. And let's say you have your section F here. So my E is vertical here. And now what we are saying is that we only know how to do the one-dimensional case. So the way in which you reduce it to the one-dimensional case is that you say, okay, let's say I'm working on charts or something like this, or yeah, let's say I fix a coordinate direction X. And now what I'm going to do is I'm just going to use oscillations along this X, right, along the co-direction dx. And what you should imagine that I'm doing is basically, I mean, right before we had like F, right? And I was trying to build an isometric curve near close to it. And what we do is we produce this H that oscillates. And okay, basically you're trying to produce kind of similar things. They just oscillate in one direction. And of course, I mean, I'm not really kind of making, okay, so this is kind of this so-called H or whatever. Okay, this picture is hard. So this is H, it's like F, but it oscillates in along the X. And of course, I'm not building H. What I'm really building is H prime, and I'm integrating, right? And I'm integrating in the direction of dx, or in the co-direction of dx. And the way to formalize it is as follows. You say, okay, what I want to do is I want to look at my derivatives, and I want to vary them in one direction. So this is exactly what this is. I'm saying, okay, take G, a first jet, which in particular it contains the first order data, take a co-direction, lambda, which is playing the role of what was here in this picture, dx. And now I consider the space of one jets that are like G, but now you've added a first order oscillation along E. And E is basically what I'm allowed to choose, right? What I'm saying is I oscillate along this co-direction lambda, and E is my amplitude. Okay. And in particular, E lives kind of in the tangent bundle of the fiber, right? I'm kind of oscillating somehow there. Okay. So now what am I saying? So okay, so here we have kind of all the possible oscillations of G in one direction, and we call this the principal subspace. And inside of this subspace, there's like the ones that I like, right? Which are like, well, kind of the one jets that actually solve my problem. And now, kind of in some sense, Gromov's theorem, I mean, you have to work a lot of work to prove it, but it's a tautological. Kind of what ampleness for R means is that every time you reduce to the one-dimensional problem, you should see ampleness. So you should just be able to solve it as we solved it before. Right? Basically, what this allows you to do is given F and little f, what you can do is you work kind of maybe chart by chart. You look in the first direction of the chart, and this replaces f by something else, and little f by another something else. But now they kind of agree. The derivatives agree in one. I mean, they agree in one direction, and then you do the secondary. You do then dx2, and then you keep doing this kind of over a basis and over all like over a covering in your manifold, and you're done. Okay. Okay. So now this is a proof. The end. So okay, let's maybe move on. I had like a bunch of random comments. I mean, basically the main comment of this slide is that ampleness is quite computable. Kind of obviously by definition it is something that you have to check for every g and every lambda, but in practice when you're working in geometric problems or like maybe topological problems, your relations are diff invariant, which means that kind of the relation looks the same in all directions. So in particular, it doesn't really matter what lambda you look at. So it just depends. You have to just check for every g. And also, if you are diff invariant, you don't have to check at every point because kind of all points are kind of the same. So yeah, you just have to check all the g's at one point, which is still some work. And in fact, in practice, it's not so easy, I would say. Right? In general, this I mean R will be given by some sort of probably some kind of the complement of some algebraic subvariety. And okay, now you have to check if a bunch of algebraic subvarieties, their complements are ample. And if you give me a dimension 1 subvariety in dimension 17, then okay, good luck. I mean, I don't know. I mean, it's kind of, I mean, what I'm saying is, okay, you can reduce it to a quite tangible problem, but I mean, the algebra or algebraic geometry involved is not completely obvious in general. Okay. So this was it. Now this was like a slide supposed to convince people that don't know about this, that this is very computable by showing to you in 3 lines that you can show that the differential relation associated to contact structures is not ample, but okay. If someone doesn't know this and they want me to explain at the end, okay, we do it at the end. Okay, so this was the recap. So let's get to the meat of this. So what is the idea with this avoidance story? So as I kind of tried to sell to you before, the point is that in practice, you start looking at relations, and actually it kind of turns out that many relations, well, they're kind of almost ample, but not quite. And what do I mean by this? So let's say I'm in J1 and I have some relation there. And again, being in J1 is not important. I could do this in general order, but okay. And let's say R is the complement of an algebraic subvariety of some codimension that I will probably take to be at least 2 in a second, just for simplicity. Then what you want to do, right, is you want to check this ampleness in each principal subspace. And what you do is you just intersect the singularity with it and just kind of let's say generically for most pairs lambda f, well, you will still have codimension D. So in particular, if this D is at least 2, then in most cases, you still have ampleness. Now, the point is now you could apply kind of some sort of Tom Bormann stratification or something kind of more like not as clever as I'm saying here. You could just stratify maybe by the dimension of this intersection. And of course, then you may be getting progressively worse intersections. But okay, let's say you stratify the space of F lambdas in this manner. And what we are saying, for instance, again, if this is codimension 2, we're saying that in the bigger strata, the situation is great. You get ampleness. In the smaller ones, maybe not. But they're small somehow. Like we're still saying, like the problem is kind of restricted to a smaller algebraic subvariety. And the question is, okay, can we use this somehow to prove an H principle nonetheless? And okay, maybe let me spend some time commenting on this. So my point a bit philosophically of why I think this avoidance story is interesting is that in the relations that I mentioned in the beginning, like contact and immersions and so on, these are different variant relations that not only are they different variant, but their solutions are supersymmetric. So an immersion, you kind of look at it from in any codirection and it kind of looks the same. And then a contact structure is pretty much the same. It kind of has a special direction, which is the annihilator, but all the others look pretty much the same in some sense. Even contact is also like that. The annihilator is special. There's kind of another kind of little subtlety with the kernel, the even contact structure, but it's also the same. Kind of they're very symmetric. So the point is that kind of like when you check ampleness, kind of this stratification is just not very interesting. But this is very special somehow. Like if you just take some differential relations in general, there's no reason why solutions would be symmetric. In general, they will be extremely anisotropic. And so what I'm saying is kind of like, we all like all these relations that are super nice, but in general, if you just do this kind of idea that we have of let's just try to list things out by rank and dimension, you just encounter terrible stuff. So this avoidance thing, you cannot avoid it in a way. You will always, for most R in a way, it will be like this. Okay, so let's say things. So what is the idea? The idea is that we are very naive. So you just do the obvious thing, right? So you say, okay, there's some G lambda, so formal datum and codirection, such that are bad, right? So we just give them a name. They are called sigma. Sigma is the space of those pairs such that we don't have ampleness. And okay, I call sigma lambda the space of G's that are bad for lambda. And now, okay, this is where the kind of ampleness up to avoidance comes. You need to assume that this is not too bad. I will be precise about this later on. But if sigma is small, whatever this means, then I mean, okay. Oh, sorry, I don't hear anything. What?
Wait a second, we have a technical problem.
Okay.
Here is okay. It must be on this machine.
Now it looks going well. So what is happening?
On the screen is fine.
It's fine here.
It's fine here too. Like what you were doing before looked pretty good. Can you?
Yeah, but it didn't change.
Yeah.
That screen.
Oh, it doesn't change that screen.
Can you just close this?
No.
So what is the problem?
The problem is with our screen here. There's something
Okay.
just in front of it.
Why not just to close it?
Wait a second. Maybe it's that computer.
Ah, there's a computer there. Okay.
Maybe it's this guy.
Oh.
Yeah.
Yes. Okay.
Okay.
Okay. So good.
Good to go.
Okay. So let me recap what I'm saying. So okay, so we have this relation R, and all we do is we kind of define this object that like contains all the bad pairs, right? And now what I'm claiming is that, I mean, okay, for this to work, you need this sigma not to be too large. And I'm not going to be very precise, but okay, maybe let me say one thing, which is that, okay, we have here this sigma lambda, which are the G's that are bad for lambda. And kind of symmetrically, I could define something like sigma G, which are the lambdas that are bad for G. And this smallness kind of means that, okay, these things should have positive dimension or have measure 0 or something like this. I will be precise later, but not now. So the idea, for instance, is that if we have a smallness, for instance, of this, what that says is I can do the following. I can go to each individual point in my manifold. I can get the formal solution at that point. And because most codirections are good for F, I can just choose a little chart, parameterized with kind of here are the codirections of the chart, such that these codirections are good for F. And now you do this at every point. And okay, let's say your manifold is compact, so you have like a finite cover by good codirections. Okay, so now in principle, you're a happy person, but not for long. Because okay, you are like, oh, great. Since due to step 0, dx1 is good for F, so we have ampleness. So I can apply convex integration once and correct the first derivative of F. And now, okay, now this happiness was short-lived because, okay, basically you've produced this F1, and sure, F was good for dx2, but F1 need not be, because you chose it just inside R. You didn't ask anything about it. So what you are like, okay, you try to be clever, and then you say, well, okay, no, let's go back to step 1. And instead of trying to choose formal solutions of R for F1, we'll choose F1 in R minus this problematic set for the second direction. And okay, this seems cool, but of course the problem is you do need this to be ample. I mean, maybe like R is ample by itself, but it's not clear that this is. So okay, first problem, but assuming it is, then you're happy, you produce F1. And now, okay, now we are in step 2, and F1 is still good for dx2, so we produce some F2. But again, problem, now, okay, F0 was good for dx3, but F1 and F2 need not be. So, okay, the way to solve it, of course, is that you do it just in one go. So you say, okay, let's forget about R altogether, and let's look instead at those formal solutions of R that additionally are good for every direction I chose in my cover. And okay, assuming ampleness holds for this new problem, then you just carry out convex integration in principal directions, and you're happy in coordinate directions. Okay, so of course, issues, as I just said, okay, we've basically carved out R by removing all these singularities. Is this ample? We don't know. But okay, at least one thing is, out of the construction I did, F is still a formal solution of this type. Okay, so but now, okay, how do we solve this? And the idea is that, okay, you just do the same thing, right? So we started the problem saying R is not ample along all principal subspaces. Let's run this argument. Now we've produced a new relation that may still not be ample, but now we can do the same. And that's what we do. So, okay, you take R, you take here psi. This is the collection dxi that I was writing before, essentially. This is the principal coordinate codirections associated to a covering. We define this relation by carving R out. And now you just iterate. And okay, so okay, what may happen, and this is what you want to happen possibly, is that stabilization happens. So there's some L0 such that this direction, so that you don't need to carve out anymore. And that would mean that basically for this L0, I mean, you've produced a relation that is ample along all the codirections given by the cover. So okay, it is unclear indeed whether this carving out process does finish, but even, well, more subtly, even worse maybe, is that the initial datum I started with is a solution of R, but I've been carving a bunch of times. So it's not totally unclear whether it's a solution of this formal solution. But, and here's the point, I mean, before I made an arbitrary choice of cover, I just said, let's pick one kind of like this. And now the idea is to say, no. What you want to do is kind of study all possible covers at once. You want to prove that this stops for all of them infinitely many steps. And then you want to pick a psi that is good for F. So you try to adapt the cover to F. And this is, okay, let's give this thing a name. So, okay, here's the theorem is common. So what we want in general is the following thing. You have your relation, and what you want is for every point in the manifold and every collection of codirections at that point. And by collection, I mean like a finite configuration, not an infinite collection or anything like this. What I want to give is a a carved out version of RP. And this I call alpha, like A of alpha. Okay. And what should this carved out version satisfy? Well, A alpha should be ample along the codirections alpha. And more importantly, for every F formal solution, F should still be a formal solution of most carved out versions of R. Okay. So, I mean, this kind of realizes the idea that, okay, I was carving out stuff because there's a few subspaces that are bad. And this kind of quantifies that, well, that it's not too much somehow, that indeed it's small in a way. Okay, and what we've proved, Xavi and I, is that, okay, if you have an open relation that admits an avoidance template, then you have full H principle because convex integration applies. And admitting an avoidance template is exactly what we call ampleness up to avoidance. Okay, so let me explain the idea. So as I said, the idea is that we're reducing to a standard convex integration, right? So this means that I start with a formal datum, and it is enough that I find indeed a cover, or yeah, codirection, a cover and corresponding codirections, such that F is still a formal solution of A of this cover, right? Because kind of by definition of avoidance template, kinda, this will be ample along the directions in psi F. And if this is a formal solution, then convex integration just runs. Okay. So all the question is how to find this psi F. And okay, maybe the philosophical remark is that the way I think about this is that what you're saying is that you're proving an H principle for psi F. And it's an H principle without pre-assumptions, or whatever Danny and Yasha call it. So, and the analogy that you should keep in mind, and in fact the proof, kind of the analogy applies to the proof as well, is that we fixed this F, and this is the same that Thurston does when he looks at jiggling. So you should think that, okay, what we do is we fix a formal datum F. What Thurston does is he fixes a distribution psi. What we do is we find codirections adapted nicely to F. And what Thurston does is he finds a triangulation transverse to psi. Yeah. And the idea is that both a triangulation and these cover with codirections, they're basically kind of data that has no homotopy information in a way. They're kind of, I mean, kind of like a cover is kind of like, it's just a bunch of opens, right? And a triangulation is a thing that kind of, right, it has no, yeah, how to say, you have like jumps kind of, or something like this in its tangent space. So this is kind of why a homotopy without prerequisites or whatever works, because there's kind of no homotopy theory behind this.
Are your sets psi sensitive to ordering?
Oh, right, yes. Well, I mean, I don't know if this is what you mean, but I mean, there's some ordering, right? So we have basically in the definition of avoidance template, I didn't write it, but we have some sort of like, if you have some, so if a formal solution is a formal solution of a carving, of a concrete carving for some psi F, and now you remove some of the directions in psi F, then F is still a formal solution. Is that what you mean? So they are ordered kind of in this manner.
But I mean, if you do it in different order, maybe it's not good, right?
No. So I mean, okay, in some sense, we don't care about the order. I mean, maybe you could improve a bit what we do by caring about the order, but in some sense, we don't. We just kind of take configurations of codirections regardless of order. Okay. But you could maybe do better like that. I have no idea, but I certainly don't know any examples where that's important. Are you happy yet? I mean, I see you as a very tiny person, so I don't know if you're saying yes or.
Fine.
Okay, very good. Okay, so let me explain to you how this jiggling type argument works. So the key thing is kind of like, much like in jiggling, kind of the local problem is trivial. So you say at every individual P, I take FP, and it will be kind of by definition of avoidance template, it will be a solution of most codirections. What this allows you to do is you can find a covering, right? Such and corresponding codirections in the covering, such that F is good for those codirections in each open. So what I'm saying is, okay, here I have the codirections here, and F is good for this U, and maybe here I have some other V, and F is good for this V. But the key observation is that even if f is good individually for each u, in the overlaps, right? I mean, kind of what we're saying is here, f is good for these two codirections. In here, f is good for these two codirections, but here we have 4. You're carving out more, so there's no reason why f would be good. Okay, so this is what I write here. And what you have to do is you just want to refine. Okay, maybe let me show you like a more dramatic problem in a way. So, or the same problem. So the thing, right, is that if you had u and v and kind of like their coordinate systems were kind of almost flat with respect to each other, then you would be back in this situation more or less, because you would be kind of like just talking about a configuration of codirections of higher cardinality. The problem is the following. Let's say you have here u, and u kind of, I mean, u thinks, right? U thinks that it is Rn. So u looks at its own codirections, and he's like, oh, these are kind of the standard Rn principle, like directions, right? But then u looks at v, and from the perspective of u, the codirections in v may be really wiggly. So kind of what your problem is that in this overlap, kind of you don't have a very nice control of what's going on, because kind of your codirections are changing a lot. So what you have to do is typical thing. You just subdivide. So okay, you just subdivide the cover, and the claim kind of is that the combinatorics of this kind of remain bounded regardless of how much you divide. And by this I mean, for instance, that the number of neighbors a ball has doesn't change. It does not depend on this I. Things like this. But even more importantly, what happens, right, is that sure, if I have some v that whose coordinate directions with this are very wiggly, seen from some neighboring u. Okay, this was actually yeah, okay, this is maybe fine. Then if we zoom in sufficiently, so if we subdivide sufficiently, now this just looks like what? Maybe like this. I don't know. This picture is terrible. Right, I mean, if you zoom in sufficiently, kind of things start looking more and more kind of straight. Maybe it's very slanted or something, but it is kind of almost constant. And what this means is that essentially, once you've zoomed in enough, when you have like the overlap of two balls, now sure, maybe red is very slanted with respect to purple, but they're essentially kind of almost fixed for directions. So now you're back in this situation. And what this tells you is that you can essentially jiggle slightly these codirections to be good for f. So okay, if you've seen Thurston jiggling, this is literally the same proof. But I mean, I don't know. I don't know how to write like a general statement that subsumes both things, but they're like extremely parallel. So I don't know. Okay, so this is the end of the proof. Are there questions about the proof? Maybe. Okay. Then let me give a few comments or punchlines. So, okay, so what we've shown is that if you have one of these avoidance templates, then basically your H principle works as follows. You first apply this jiggling H principle thing, and then you apply standard convex integration. That's it. Now, you may wonder, of course, how hard is it to construct an avoidance template? And my claim is that it is pretty much the same as checking a standard ampleness, except that you have to be more stubborn. So, right, so what you do is you take your relation, you check ampleness, and if you just want to apply Gromov, then when you see that ampleness fails somewhere, then you're like, I'm sad, and the end. But if you just try to do what we do, you just say, okay, sure, okay, I've checked ampleness, it kind of fails. Let's do carving. Okay, I check again. Am I ample? Okay, oh, it failed again. I carve it again. So it's kind of, you just check ampleness over and over until you hopefully succeed. Okay, so let's say computationally, it's not very different from the standard thing. As I pointed out before, this argument, what it does, right, is that we're constructing relations inside of R adapted to each F. In particular, what you should note is that even if R was a vibration, there's no chance that this is a vibration, because you're carving out, kind of depending on the cardinality of your cover of the intersections, you'll be carving more or less in general. So probably this is just terrible. It's a terrible thing.
Can I ask a question?
Please.
So in the parametric case where the formal solution varies, this doesn't cause any problems?
Yeah, so okay, let me jump. Here it is. So the parametric case follows from the standard one, and it's the typical trick. So you say, okay, if I'm looking at k parametric families, let's look at the product manifold m times k. On top of this, I have r times k. And out of this, I mean, let's say if for r, I had a template, and the claim is that r times k inherits a template that you can just call a times k. So essentially, I mean, maybe let's say like this. So for a parametric family, you carve out in a manner adapted to the whole family at once. And you don't have to reprove anything. It follows from the non-parametric step just by doing this multiplication. You're happy, Danny, I guess?
Yeah.
No? Yeah. Should I say more, or what is your complaint?
No, it's fine.
Okay. Right. So okay, that I wanted to say, so that's good. Yeah, so the comment I was making, right, is that okay, this is not even a vibration, so this is definitely not different variant. It's probably not ample, but it's certainly ample in coordinate directions. And okay, Yasha and Misashev had this question in the book that is kind of a funny question. Yes. Is there a geometrically meaningful relation that is ample in coordinate directions but not ample? And okay, I mean, this is like a Frankenstein of a relation, but okay. I don't know if, I mean, it's geometrically meaningful, I guess, if R was geometrically meaningful. And I mean, more importantly, I mean, we have examples now of ample up to avoidance relations that are not ample. So that's nice. Okay, kind of obvious comment as well is that, okay, you're running this argument, right? And at some point you may just fail, right? And that would mean that you've tried to check ampleness and ampleness fails. And examples, of course, are whenever H principle fails, of course, this must fail. And for instance, what you can check, I think that if you apply this kind of once to contact structures, then you get the empty. So kind of you carve everything out. And for functions without critical points, you basically, after as many steps as the dimension of the manifold, you carve out everything. The idea is that you can imagine that the singularity, right, for no critical points is the zero covector in cotangent space. And every time you do one direction, kind of your singularity spreads out through that codirection. So it's kind of after one step, it's one dimensional, then it's two dimensional, and eventually you've carved out everything. And in general, I mean, this I find kind of cute. I mean, it's obvious, but if your target, if the fibers are one dimensional, then this will happen in general, unless unless it's like a trivial relation, right? Basically, yeah, the ampleness cannot hold for one dimensional targets. And so you always carve everything. Okay, but okay, this is just supposed to be made like a controversial statement or something like this. So the idea, right, is that when you're trying to apply standard convex integration, the thing is like what you really like are thin things, right? Which means that in every principal subspace, you should be codimensional. That's the easiest case, right? And at least a moral statement, I think, is that in some sense, maybe one should try to think of thinness as having codimension 2 globally, as long as the target is codimension 2. I'm not saying this works always, but I'm saying that if you have a problem like this, you should call Xavi and I, because it looks good. Yeah, that's all I want to say. And okay, maybe, yeah.
But this statement about codimension 2, like is that generically this also always sample, even this is written in Gromov book, right? So that, can you give some more kind of like more example when it's kind of applicable or some kind of
So I mean, in some sense, indeed, that comment is exactly what you're saying, but I'm gonna give you like now a codimension 1 example. Okay. So that is more interesting. Okay, and maybe okay, this is a really fast comment. So all I'm saying is ample up to avoidance is more general than ample, but in some sense it's still a particular example of what Gromov does, of the machinery of convex full extensions. So okay, I don't want to say much, but I mean, basically the point is the machinery of convex full extensions is so general that whatever you want to do based on the one-dimensional convex integration we did, it must always live kind of inside. But the point is that the most general definition of being ample in the sense of convex full extensions is like completely uncomputable. Kind of saying that something is short in the sense of Gromov is something that you can never check because it's not pointwise. But these conditions are pointwise. So kind of what we're doing is not so much about generalizing Gromov, it's more about kind of providing computable criteria for relations. Okay, so okay, Yasha, now I'm gonna try to make you happy. Let's see. So okay, our main application is the following. So we look in dimension in 6 and rank 4, and we're looking at maximally non-integrable distributions. I'm gonna tell you what this is in a second. And we do it as follows. So you say, okay, I look at a distribution psi, and at least locally you can express it as the kernel of 2 one forms alpha 1 and alpha 2. And now to check the non-involutivity of psi, what I do is I look at the differentials of the one forms, and I restrict them to the plane. And this is, well, it's on pencil of 2 forms, but I mean, these are like kind of like the curvatures of the distribution. So they tell you kind of like, if these things are non-degenerate, then basically this is non-involutivity. And okay, how do you measure this more properly? Well, what you say is, okay, if I have 2 forms, to check their non-degeneracy, what I do is I just take their wedge with themselves. And this basically outputs a number up to the choice of a volume. And what we're saying basically is that we've defined a quadratic form in this pencil. And now there's essentially three situations: either the pencil, I mean, either the quadratic form is degenerate, or the quadratic form is definite, in which case we say psi is elliptic, or the signature is 1, in which case we say that the distribution is hyperbolic. And of course, these 2 cases are kind of like the generic cases, and this is what I would call maximally non-integrable in 4.6. And okay, I cannot give you an answer. Well, okay, maybe I will, in the last slide, maybe I will make a comment, but I mean, it is indeed not completely obvious. I mean, I cannot give you like a recipe that works for every k and n of what maximally non-integrable means. But if you give me a concrete one, I can try to work it out. It's kind of the point. But okay, in this case, it's this. And okay, I'm kind of running out of time, so let me just kind of give you the punchline.
How is related to growth of like bracket generating spaces? Kind of how fast they grow.
Right. So this is much stronger. So growth. I mean, let me say it like this. Wait, am I lying to you? Let me think. Yes, so I could have a rank 4 distribution that is bracket generating, but it's but the quadratic form is degenerate. So this is strictly stronger. A typical example would be something of the type kind of one of the curvatures would be like dx1 dx2, and the other one is like dx2 dx3 or something. These are like linearly independent, so that means that you are producing 2 different directions, but they don't span a nice pencil. Does that make sense?
Okay, well, go ahead.
Yes. So yeah, I didn't hear yes. So you said okay. 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 So okay, let's not maybe get into super details, but I mean the point is that basically you try to run the argument we did. I mean you try to construct this template, and what you will see. Well, okay. Let me give the statement. The statement is the H principle applies because we can construct a template for these things. Do note that this condition is indeed for dimension 1. Right, this is basically some determinant has to be non-zero. And the punchline basically is that when you run the proof, okay, let me just do the picture. So what you encounter is the ampleness of the hyperbolic condition is equivalent to the ampleness of the outside of this cone. And the idea is that I think, let me try to remember, this 3-dimensional space represents the space of symmetric matrices. Right, so the space kind of quadratic forms, and so okay, so the ampleness of the outside is kind of the reason why hyperbolicity is it abides by H principle, and the inside corresponds to ellipticity, and it's why elliptic it does not satisfy the H principle. Well, I mean, okay, we don't know if it does, but certainly convex integration fails really badly. And the point is, this is the generic case. This happens for most lambda f, but there's a smaller subset where you see the typical problem that you have a singularity of dimension 1, and hyperbolicity means that you are here, and this is exactly what you try to avoid. And what happens? Okay, let me not show you the computations, but the point is that you basically have to run the avoidance argument a couple of times, and in fact, the second time is not exactly what I told you; it's slightly more refined, but okay, it works.
Well, can I explain? Because kind of it looks like that hyperbolicity, that ellipticity is open condition. So how come it's just coordination? Yeah, you want to avoid this ellipticity, which is kind of like open subset.
Right. Right. I mean, so I mean, there's three components. Two of them are elliptic. The outside is hyperbolic.
Yes.
So my formal data is okay. Maybe I should stop at the statement. The statement is there is full H principle for hyperbolic, and convex integration is really bad for elliptic.
Okay.
Sorry. Yeah. Okay. Now I understand the confusion. Yeah. So indeed, elliptic is kind of. I mean, okay. In our fantasy of trying to pinpoint where rigidity may be, my claim is elliptic. It's kind of interesting, I think. And hyperbolic is not, but it did take some work. So okay, let me just give a bunch of comments, and I will finish. I'm sorry, I'm over time. So okay, now that kind of this is done. So by the way, the paper is essentially done. We wanted to upload it before the conference, but we ran out of time. So this basically we just want to add pictures, so you can expect it in the archive in a couple of weeks. And we just go through this hyperbolic stuff. After this, something that we're doing, Chavi and I, together with Igor Salenko, who's a sub-Riemannian geometer, is we're now trying to just systematically kind of apply these ideas to just go through K and N. And okay, basically, I mean, Igor is kind of helping us a lot with this because kind of he understands quite well exactly what maximally non-involutivity should be. In particular, let me make the following. Oh yeah, so we have this concrete conjecture, which is the following in corank 2. There's basically the following cases. There's angle, which is a special because you need kind of 2 brackets to do it. So it's kind of outside of this thing. Then there's odd rank. And here you have ampleness in the standard sense, but it's actually not so easy to prove. I mean, this does take a lot of work. And Igor had to like, I mean, he's kind of teaching us kind of some pretty hardcore linear algebra. I mean, I don't know. It's kind of beyond my comprehension still at this point, but okay, it works. And in the even rank case, of which 4-6 is a concrete example, you have this elliptic and hyperbolic thing going on. And the claim is that this should be flexible due to avoidance, and ellipticity in general should just, I mean, it's just not ample. So, okay, maybe there's rigidity here. And okay, funnily enough, I had like a heart attack yesterday morning. So I kind of woke up and went to the archive. I half sleep still in bed, and I saw the following title: Existence and Classification of Maximally Non-Integrable Distributions of Derived Length 1. And I was like, oh my God, this is literally what we're doing. And I opened the paper, and now, okay, now I'm kind of, okay, now I'm okay. But I mean, yeah, maybe don't read papers when you're like half asleep. So the point is this. So Adachi, it's very nice. So I mean, Adachi's he has the same obsession that we have, which is that he's also using convex integration to also study maximally non-integrable distributions. And he focuses on the odd rank case, and he provides an H principle, basically, yeah, using standard ampleness. But, and now this is kind of where your question about what maximal non-integrability means, it's a good question, Yasha. So what he calls maximal non-integrability is less maximal than what we call maximal. Okay, yeah, so basically, I mean, okay, I would argue that the natural notion of maximal is what we consider, and it is indeed more restrictive. And indeed, I mean, in the odd rank case, as he does, it follows from convex integration anyway, but it's just slightly more complicated, I would argue. But okay, yeah, I mean, you should check this paper out. And okay, and last comment, I'm done, I'm sorry, is that right, I mean, so we've been saying that this elliptic things, convex integration, even in this sense, it just goes badly. But this is hardly a surprise because elliptic distributions are what you would call fat, which is that their sphere annihilators are contact. So that means, for instance, in the 4-6 case, out of every 4-6 compact manifold, you produce a contact manifold of dimension 7, also compact. It's an S1 bundle on top of this. And I mean, I don't know. I mean, so I think a really nice question, but I think it's maybe also hard, is can you use contact topology to study this? And of course, the issue is that, okay, in dimension 7, I think it's hard to do things, especially for me, because I'm very ignorant about rigidity. But I mean, okay, I have like a master student, Nina Rutten, and what we're trying to do at least is try to construct more examples of these things, understand how they contactize, trying to construct examples of pre-Legendrians, so things that live to Legendrian. And I mean, maybe at least for Legendrians, maybe there's something to be done. I don't. I mean, kind of try to use the rigidity of Legendrians to prove something about these pre-Legendrians. But okay, I can't tell you anything concrete. I just think it's a nice problem. And this is the end. Yeah. Thank you.
Thank you.
So there are maybe over-twisted distribution of dimension 4 and 6 space, right?
That would be very nice. Yeah. Yeah. I mean, so for instance, something that I've been discussing with Igor also, but I think, I mean, okay, so something we've been trying to do, discussing a bunch, was trying to understand 4-6. I don't. 4-6 is kind of, maybe let me say like, so somehow for rank 2 things, I have the impression that I know how to do stuff. And the idea is that I have the impression that you could prove over twistedness for every maximally non-integrable rank 2 distribution, much in the way that you proved it for contact 3 manifolds in 89, and that we proved it for angle. So for 2-3-5, for instance, I think I know how to do it. And I would think that I know how to do it in general. We've been trying to, instead of producing over twisted disk, we've been trying to follow the original angle paper we did, but that seems doomed, I think. So you really need to do over twisted disks. But for 4-6, kind of the problem is that 4 is too big. I don't know how to do things with more than 2 directions somehow. And maybe what one has to do is then kind of look better at your paper. Yeah, so Yasha Emi with Borman. And then, yeah, maybe one can try to do things. I have no idea.
So what happens to your method for angle structures?
Oh yeah, angle is bad. So angle, right? So angle is a second order relation. And upon freezing the first and 0 order, it is linear, which is bad. Basically, I mean, it just fails kind of much like contact fails. Okay. So if one wanted to do something like this, one would need to come up with some sort of convex integration scheme that kind of uses smartly kind of the 0 first and second jet at once. Maybe that can be done. I don't know. This is something that I would be very curious about. But yeah, so yeah, this can do nothing for him.
So if you take the Adachi version of maximal, is the elliptic case as bad as for your version?
So let me think. So I mean, Adachi's okay, yes. So Adachi still works in odd rank, so there's no ellipticity for him. So in odd rank, there's kind of a unique kind of situation. Well, okay. So in even rank, there's this dichotomy kind of thing, and not even for all even ranks. It's only for the multiples of 4. But in odd rank, this is not happening.
And for hyperbolic ones, you have like hyperbolic ones of different indices, sort of, yes. But they're like all flexible is the point? Or?
Well, that's what we should, I mean, it's okay. So for 4-6, we kind of went through this kind of algebra to construct the template. And yes, I would conjecture it is the same, but it's just the algebra becomes so terrible. So this is kind of why we're hoping Igor will save us.
I'm just trying to understand that kind of tensor, all the different tensors.
No, but you're absolutely right. That's the case. It's like an index thing. Yeah.
Okay. But they're just kind of all flexible. That's how to be a lift.
That I would think so. Yeah.
So no more questions. Thank you very much.